presentation about the most recent result on supermassive black holes, and in particular, if this guy, okay. So typical, okay. So here is what I will talk to you about. First of all, how do you actually make an observation of supermassive black hole? This is something that I didn't know about. I had to learn myself because I'm not an observer. Then I'll tell you about how you, once you have an image, how do you convince yourself you're looking at a black hole and not something else? And that's where, you know, the theoretical part comes in and my work really comes in. And then comparing theory and observations to deduce some properties. And most of this will be very general for generic black holes. But then I will start telling you a little bit about, it will be generic, but mostly focused on M87. And then I'll tell you what are the differences when you start looking at Sagittarius star. And because I'm interested in gravity, then I will tell you also about alternative to Einstein in terms of gravity, in terms of theories of gravity, or to black holes. You know, what we see is, are we sure that it's really a black hole and not something else? There are these other objects, black hole mimickers, that are very similar, have similar properties. Okay, so first of all, if you're asking yourself, how do I take a photo of a black hole? There is a very basic problem that you have to think about and solve. And it's as follows. Black holes are the most compact objects we know in nature. You can't make anything smaller than a black hole, given a certain mass. The second problem is that they are at astronomical distances. That means they are, you know, naturally very far from us. So you take something which is small intrinsically, which is very far from us, on the sky will appear as extremely small. That's why we don't observe, you know, stellar mass black holes, although they are in our galaxy. So what you need is that whatever black hole you have in mind and you want to look at has to be of a size such that you can resolve it. And when you consider all of these constraints, essentially there is just one solution to this problem. You want to have the biggest possible black holes, and that's not enough. You want them to be at the right distance so that you can measure it, their properties. Because, you know, with the best of our technology, we can get something of order 50 microarcseconds. You need a black hole that has that size roughly on the sky. And you go through your list of black holes and you find out there are two candidates that match these requirements. One is M87 star, the other one is Sagittarius star. M87 star is much bigger, billions of solar masses. Sagittarius star is millions of solar masses, but they are different distances. So at the end of the day, as I'll show you, they look roughly of the same size. And that's it. You know, we don't have many other candidates. If you look at the other ones that come down in the list, these are at least a factor 3 smaller. So nothing you can look at right now and maybe from several years. Okay, so let's have a look at M87, which is this galaxy. In the optical, you see it's an elliptic galaxy. It doesn't have anything, you know, particularly striking, apart from a jet that comes out of it, this filament. Now, if you look at it at the same object in the radio, you find out it's actually much bigger. There's a lot of excited plasma that is emitting radio waves. And, you know, radio astronomers have been looking at this object for many, many years. And they have developed techniques which allow you to have smaller and smaller zoom-in images. So you can, if you look at centimeter wavelengths, this is the image you get M87. You can start seeing very clearly that there is a jet, and that there is a jet, a counter jet that is producing something. You can zoom in this part over here. This is over the order of 3 light years. You can further zoom in at the base of the jet, and you know, people know very well all of these. They know every single spot. So they study how these spots move in time, and that's how you understand that actually there is close to the speed of light propagation in the jet. And to give you an idea, this is the resolution that you need, and we have obtained with the Event Horizon Telescope. So it's about a factor 10 smaller than anything we had done before. How do you do this? Well, it's this technique, which is called VLBI, very long baseline interferometry. And it's essentially, to understand this, you have to remember, you know, an equation you've probably seen in your first course in astronomy that says that the resolution of an astronomical observation is given by the ratio between the wavelength at which you make the observation and the size of the telescope at which you are collecting the light. Now, if you are naive, you think, okay, I need this number to be small, so I take a small number here and I'm done. I can take gammas, okay? Well, it doesn't work like that, because most of the gamma or the X-ray or the high energy radiation is blocked, doesn't reach us. So what you want is radiation that reaches us, and as it happens, this is radio waves. And not only radio waves, you need radio waves that are not scattered too much by the interstellar medium. So at the end of the day, what you have here is 1.3 million. What you want to have here is 50 micrograph seconds. And so at the bottom here, you need to have a telescope which is as big as the whole planet. And that's the idea behind the Event Horizon Telescope. Build a telescope, which is a virtual telescope, which is having a baseline of few thousands of kilometers. So how do you do this? Well, you collect radio telescope. There's a very nice telescope in Spain, in Pico Veleta. And you put them in an interferometric pattern. So for instance, between one in Arizona and one in Hawaii, it's about 2,500 kilometers distance. And you can therefore create this technique. And now, if you think a little bit about this, you find that this sounds a bit strange, right? How do you actually produce, or just putting two telescopes together, why should this produce a coherent image? What is important is that you're making the observation at exactly the same time. And by exactly, I really mean exactly. So you really have to guarantee that the wavefront that you're measuring is exactly the same. How do you do this? Well, you have to make sure that while recording the radio signal, an electric field, you're also recording the time of arrival with nanosecond precision. So you have atomic clocks. All of these telescopes have atomic clocks. They can record the signal and the time of arrival. And then you collect all the data and you combine it. And then you can do interferometry. Why do you need many? Well, first of all, as I'll explain in a second, having different baselines allows you to have different wavelengths, not wavelengths, but scales, length scales over which you can produce an image. But also more practically, the Earth is rotating. So if you want to observe for a long time, then you need telescopes all the time so that you can actually do these observations. And this is the present network of EHT telescopes. So let's try to understand this a bit more in detail. You have telescope with different baseline. I have color coded them. Each baseline represents a track, a given color in the UV plane. This is essentially is the two-dimensional Fourier transform of the intensity in the sky, I. And as you have, so this space in principle has to be filled with colors. And once you have a partial filling, what you have is an image, which is not a perfect image. This image is resolved at different scales, and the scales are the ones given by the different baselines. And if you wait long enough, you can populate this more. Okay, so after 8 hours, you see these funny stripes that we have in UV plane, and then you have a certain image. That's what we have essentially done. So you start with the very first baseline. It's got essentially, you just have a single stripe in the UV plane, in the image plane, and then as you put in more and more information, you can have and build an image which is sharper and sharper. And you need to have at least 8 hours so that you can fill this space sufficiently enough so that you can get some image. These are the images we took of M87, and we published in 2019, 3 years ago. And as you can see, they are different. So we observed 8 days. 4 days were just not good enough. But for days, we had enough coverage. We had enough telescopes that could see the sources. And these are the images we produced for the different 4 days. They are similar, they're not identical, and it's very important. Mm-hmm. That's what we expect, and I'll get back to this later on when comparing with the Sagittarius system. Now, essentially, we were given these images from our colleagues saying, okay, now tell us what is this? Why does it look so funny? And to do a theoretical interpretation, essentially, you need 3 steps, logical steps, and then also mathematical. The first one is you have to calculate the dynamics of the plasma near a black hole. We call this GRMHD, generativistic magnetoaerodynamic simulations. Then you have to ray trace the light emitted. So this first step just tells you what happens to matter as it wants to accrete near a black hole. The second step tells you, okay, now this matter is emitting light. How does light gets absorbed and emitted and does cover funny trajectories before reaching us? And in this way, you produce synthetic image. And then you have to, the third step is adding a lot of synthetic images, which are mathematically correct, physically consistent, you know, compare with the observations. We were very lucky that the ERC gave us a lot of money for this project, Black Hole Cam, to me and my colleagues, and we managed to build an infrastructure, computational infrastructure, to do these basic steps, and now this is further continued in this other ERC project, JetSet. The real heroes of this story are these guys over here who have, you know, essentially built all of this infrastructure, and they are now no longer in Frankfurt. They are filling faculty positions that were in a number of places. So as a theorist, I think about a problem in terms of the equations that the problem can be described with. And these are the equations I have to solve. So these are conservation equations. These are essentially the generativistic magnetoaerodynamic equations. I have actually put together. The energy momentum tensor is the energy momentum tensor of the whole system. So fluid plus electromagnetic field. This is a covariant derivative. So I need to have a curved space-time. I can be, you know, Kerr black hole, but it can be anything else you may want to consider. And then you need to solve the radiative transfer equation, which is essentially a Boltzmann equation for the radiation field, which is described in terms of this quantity, which is the intensity. This is a frequency integrated quantity. And then this object over here, you have to calculate it along the right trajectory, the geodesics that the light will follow in this spacetime. So let me give you an example of how this works. And this is the first step. This is a magnetoaerodynamic simulation. You're seeing here in red and yellow the plasma density, and in blue white you see the magnetization, essentially the strength of the magnetic field. And what you can see, this is the result of a simulation, is that first of all, matter doesn't, you know, that produces a kind of a torus, and in the vertical direction, you have mostly magnetic field, very little matter, but a lot of, and very strong magnetic field. But all of this is very dynamical. It's not a, you know, the kind of picture you see in textbooks where the jet is perfectly symmetric and the mass is perfectly accreting. There's a lot of variability because the flow is triggered by an instability, the magnetorotation instability. This is the inclination at which we think we're seeing M87. And now we go from GRMHD to radiative transfer. So this is the light that you would observe if you were sensitive to radio emission at 1.3 millimeters. It looks like a ring of light. It's not quite a uniform ring of light. And this is because of a Doppler effect I will explain. But this light field is actually very complex. If you start rotating around it, you see that, you know, it will produce a different shape depending on your inclination. And this is the same synthetic image as would be seen by a radio telescope like EHD, okay? You will see a funny looking ring which flickers, and that's what we have seen. Now, you all know how to use a pointer, okay? You press a button and light comes out. The reason why it is so trivial to use a pointer is because we are in flat space-time. I know exactly where the light is going to point because I know that the light will propagate in a straight line. But in a curved space-time, this is very different. I could point in that direction and the photon could go in that direction. Trajectories that light is doing. So just to give you an idea, take a black hole, take a disk of light or matter emitting light, and imagine to take a photo of this disk. What you will see first are the photons which are moving directly in straight line towards the photographic plate, And so you would see, the front part, just like you see the front part of myself, you would see the front part of the disk. But there's going to be photons that, if you shoot them vertically, they can actually be bent and reach you. So you can also see the back of the disk. It's like you can see the back of my shirt. And more interestingly, you can even see the bottom sheet of this light ring. So you probably have seen this picture. This comes from Interstellar. It's almost right. It's not quite right. There are a few things which are wrong, but now you understand why it looks like that. This funny shape is because you see the part of the disk in front of the spaceship, and you see the part which is behind the black hole, and this is the part of the disk, the bottom part of the disk. You also see this funny ring here. This is called the light ring, and I explain that in a second. What this explains to you is that if you have to hide, don't go behind a black hole. It wouldn't help, right? You would be seen anyway. Now, what is wrong in the Interstellar is that the disk is not thin, but as I said, it's thick. So you have to think about a donut. And this donut, the way it will appear will be different according to an inclination. You see that you will see two black regions, or you will see a single black region. You will see a uniformly bright region if you see it from the top exactly. So the appearance of this radiation field will depend on the inclination with respect to the observer. And we don't know what is the inclination. But one thing that is always present, unless you consider this extreme cases, there's always a bright spot, a bright side. That's because light from that side is boosted towards you, and so towards the observer. In this case, the observer is over here, and so the observer will see a bright spot. Now, this guy here, we call the shadow. This is not, well, it's an indirect evidence of the presence of an event horizon, but it's not the event horizon. The event horizon is much smaller than this dark region over here. And to explain what is a shadow, let me give you another example. Suppose that you have a black hole and you have a source of light, okay? So this guy is going to produce photons, which will reach, some of these will reach the event horizon and be absorbed immediately. But some will not reach the event horizon and yet be absorbed because they are within the light sphere. It's a surface such that it's within the unstable photon orbit, which is something you study when you study geodesics in Schwarzschild. And any photon within this sphere will eventually be trapped. So if you are an observer over here, you will see a deficit of light. All of this light is missing because, well, has ended up in the black hole. But it is larger than the event horizon itself. To be more precise, the event horizon in Schwarzschild is twice the mass. The photon circular orbit, the unstable photon circular orbit is 3m, and the shadow is the projection at infinity. So it's the impact parameter at the circular orbit, and this is square root of 27, which is roughly 5.2m. So the shadow is about a factor 2.5 larger than the actual event horizon. The shadow doesn't have to be black. The event horizon is intrinsically black because you can't get any light. But the shadow is just a deficit, because if I take a photon here and I shoot it towards the observer, that photon wouldn't have any problem reaching me, right? Because why should it be trapped? It's just if it goes in this direction, it is trapped. But if there is matter here that is shooting light, then this light can be propagated. That's why in the shadow we observe is not black, but there is a depression in intensity. Okay, so what are the spatial parameters? If you want to study this problem in generality, you have to think about, well, exploring all the possible spatial parameters. So you have the black hole mass and spin. In the case of M87, we didn't know the mass. In the case of Sagittarius star, we do. But of course, we don't know the spin. We need to consider maybe black holes in other theories of gravity, maybe alternative to black holes. You can have objects which have a light ring and a light sphere, so a shadow, but maybe they don't have an horizon, or maybe they even don't have a surface. I will explain some examples. Then we don't know what happens to we have some model for triggering the accretion, but these are models which are not unique. we don't know exactly what is the strength of the magnetic field. And so we know that depending on the magnetic field, you have two main families of accretion flows. One is called the sane, the other one is called the mad. This guy is magnetically dominated, and so has a slightly different morphology in the disk and in the jet. And then you need to understand what produces the light, what are the properties of the production of the light. And this is the most delicate of the problems. Let me explain you why. So we know that we get light at 1.3 millimeters. This is radio, has to come from synchrotron radiation. So electrons going around magnetic field lines. But the properties of the synchrotron radiation, the intensity, will depend on the energy distribution of the electrons. And we have no idea what is the energy distribution of the electrons. Our simulations don't evolve the electrons. It's a single fluid, and what we really evolve is the most massive part of the fluid, of the plasma, which is the ions. So we can calculate what is the energy distribution of the ions, but then we have to connect it to the energy distribution of the electrons. So what distribution? Well, you make yourself your life easy and you say it's a thermal distribution. But then you still need to give a temperature to the electrons. And this, what you have is the temperature of the ion. So what you can do is you calculate this guy systematically, consistently from your simulation. And then you say that TE, the temperature of the electrons, is given by this very simple formula, which has, essentially two parameters, although one is not really a parameter. This is the beta, plasma beta. It's the ratio between the gas and magnetic pressures. And essentially it's a way to place electrons in the jet or in the disk. If you put, beta going to 0 is essentially in the jet, and beta very high is in the disk. So this distributes the electrons in different places. And R high is really a free coefficient, which we consider between 1 and 160. And large R high would correspond to essentially electrons in the disk. So cold electrons, while this one would be electrons in the jet. So it's a formula. It's an analytical formula that we use. Is this right? Well, it's not right, because it's, as I said, it's coming from a number of simplifications. But we've done other studies, more sophisticated, where we had, not used the thermal, non-thermal energy distribution coming, for instance, from turbulent heating or magnetic reconnection. And what you find out at the end, because it's such a simple formula that covers all the possibilities, essentially, this covers also more complicated physics. So that's what we use and continue using. Then you have to make a lot of simulations. About half of them were done in Frankfurt. Out of these simulations, you build scenarios, depending on how you distribute the electrons. Just to give you a sample of the library of simulations that you can produce, you can get very large shadows, very small shadows, the disk going in one direction, in the other direction, a very extended disk. You have all of the possibilities, and then you have to consider all the different angles. These are all seen face on. Determining where the light comes from is essentially impossible. So when I get an image, an observation image, I can have that light coming from many different places. To explain this better, suppose that I have these 4 images. These are coming from 2 different MAD simulations. So these are, R high 160, high 10, and this is the same.
Excuse me.
Yeah.
The 3 parameters in your simulations are temperatures and the mass of the...
So no more than temperatures are these. These R high and R high is really the free parameter, and then of course, I mean in terms of microphysics, okay, is R high, but then I have MAD or sane, which is the magnetic field, and then I have the black hole properties, mass and spin.
Mass, magnetic field, and temperatures.
And spin. Yeah. So okay, let's take these 4 images. These are, physically we don't know which one of them is right. They're all potentially right. but they correspond, if you want, to the corners of the space of parameter when it comes down to magnetic field, because magnetic field distinguishes these guys from these guys, and the temperature distinguishes, this guy from this guy, or this guy from this guy. And what you can do, because these are synthetic, you can split the image. You can say, okay, let's just make an image with all the photons coming from the disk, or those photons coming from the jet, the one coming towards us, or the jet is going away from us, okay? And when you do this, you have essentially this matrix here. And you can see that for MAD, it's mostly coming from the disk, and there is a little, I don't know if you can read the number, but this is the percentage of the image that is produced by the near side, that the jet is coming towards us, or the receding jet. Okay, so even the receding jet is producing some light in this total picture here. And depending on the physical conditions or the thermodynamics, you can have actually that it's the receding jet that is producing most of the light. The majority of the light comes from the receding jet. The bottom line is that if you have just these objects, and if you have just observations, it's very difficult to tell where the light is coming. And that will bring in some degeneracy, as I will explain. So then we build synthetic images, 60,000 synthetic images, and then we have to compare the 60,000 with the 4 images we had produced through the observations. How do you do this? Well, very algorithms which allow you to these data sets. Ah, right. I am with wrong. Should I?
There is this cable here.
Try and.
Oops.
Yeah. Yeah, I need another adapter.
Yeah, they here they have one. Yeah, it does work.
Okay, maybe this should work. Okay, so to explain how you do the matching between data and models, imagine you take a snapshot. This is a single snapshot of a DRM-HD simulation, then you deconvolve it to reproduce the visibility of the EHT. And this image you can deconvolve, as I explained, in this Fourier space, and you have this the visibility amplitude and the closure phases. These are the real and imaginary part of the Fourier transform. And so the model here is the green point. So you can think that this image gives this green distribution, and the blue are the data coming from the image you have recorded. So what you do is you scan through your simulation, you produce varying model points, and then you just do a chi-squared statistics of which image fits best your observations. I always have problems explaining this because we tend to think in terms of images rather than visibility. So if you want an analogy, imagine you go to the stadium and the stadium has 60,000 people. And you have a photo of someone that you think is in the stadium. You don't know anything about this person. You just know that maybe he's in the stadium. And so what you do is you scan this photo against all the people who are in the stadium. And the software will start picking up potential matches. And then you ask the software, so is this person in the stadium? The software will say, I don't know. What I can tell you is that I have 10 people that look similar, then you decide. So, also in our case, we don't have the certainty that our model matches the observations, but we have something important. What we know by this exercise is that this person most likely is a woman with long hair, because all of the, people that have been matched are women with long hair. So certainly it's not someone like me, okay? And that's the kind of logic you have to understand. When we compare with the observation, we can just find the models which best match and understand what are the properties of these models. And these properties are robust, then we are confident about what we found. If the properties are not robust, then we cannot say anything. So here is an example. Okay, these are the observations. It is a model that matches very well the observations. Of this model, we know everything: the mass, the spin, the properties of the electrons, the temperature, and everything. And you would say, okay, if you know everything, they look so similar. Obviously, you know everything about the source. No, you have to be careful, right? Because as I explained, it's like the match I was giving before. And in fact, I can give you 3 examples here which match the observations equally well in this measurement, in this gauge, but they correspond to completely different objects. This is a counter-rotating black hole, so this is a Kerr black hole with negative spin. This is with a positive spin, almost maximally spinning, and this is a Schwarzschild black hole, 0 spin. And yet they produce the same image because I have so much freedom in placing the electrons that I can get essentially the same image. So this is good and bad. It's good because you convince yourself, okay, just like in the example of the woman, it's a woman with long hair. Here you can say it's a black hole. But then you don't know exactly what are the properties of the spin because you are blind to the spin. You're not able to tell the difference, at least with these simulations and these observations. Okay, so all of this is pretty generic. And all I said is true both for Sagittarius A star and M87. So what are the differences with Sagittarius A star with respect to what I just said? So these observations, we've taken the observation at exactly the same time. The same night in 2017, we were observing M87, we were observing also Sagittarius A star. And it's the first object we looked at, okay? We wanted to look at Sagittarius A star first, but then we realized that actually there are a number of complications that come with this object. So a number of disadvantages and a few advantages. Let me explain what these are. The first important disadvantage is interstellar scattering. So in M87, you just point out of the galaxy plane and you go to the Virgo cluster. So you don't encounter much within the galaxy. If you want to look at the center of the galaxy, you have to go through all of the galaxy and all the plane of the galaxy. You're going to collect a lot of scattering. And this is just to give you an idea about, this is a simulations with scattering. You start seeing things, microstructures. You don't have a very sharp picture anymore. And on top of this, so this is, still a theoretical image. You have to imagine that there is also the blurring coming from the actual telescopes. So scattering is a problem. Then another most severe problem is variability. The variability goes with the time scale of things happening will go with the mass of the black hole. So if you calculate what is the time scale, in the case of Sagittarius A star, it's about minutes. In the case of M87, it's about days. That's why they look almost similar on different days. But you have to take 8 hours, as I explained. So you have to take an exposure of 8 hours for something that is changing every 8 or so 10 minutes. It's like, taking a photo of something moving very fast. And then, as I explained, the UV coverage, the way we sample the UV plane is incomplete. You have to imagine that, this is like having a telescope with holes. You can only get some information from some parts of the telescope and not everywhere. The error bars, because of the variability of the system, are also very large. So at the end of the day, there are many, many, many images you can build that are compatible with the data. In fact, 9,000 images which are compatible with the data. When we try to explain this to the people of the HT who are in charge of explaining what we found to the public, so the public outreach group, we had problems. We could not explain, or people could not understand, how can you have 9,000 images if you have from the same data? So I've come up with this analogy. But yeah, maybe I should first tell you about what is the additional information. So we know the mass very accurately. This is the mass of Sagittarius star. We know it with 0.2 precision. So this is far better than what you know your weight. I don't know how many of you know your weight with a precision of 100 grams, but essentially that's the precision we know the mass of M87, of Sagittarius star. Also, is an object we've been looking at in many different wavelengths, in the radio at these frequencies, in the infrared, in the X-rays. And we also been looking at these objects while we were taking the radio. So we have the light curve at 1.3 millimeters, the variability on 3-hour intervals. We have the variability of the visibility amplitude at 4 gigalambda. These are all additional constraints that need to be imposed. So all in all, we have 11 constraints, and this allows us to have, although there are disadvantages, these are the advantages that we have, and allow us to have actually a much more stringent selection of models. So here is the analogy I was telling you about. I don't know how many of you recognize these peaks, but if you've been walking in the mountains of Italy, the Dolomites, these are called the Le Tre Cime di Lavaredo, Drei Zinnen in German. These are 3 peaks, and this is a time-lapse movie of a typical November day in the Dolomites. So early day, there's a lot of cloud coverage, there's even some snow. Sun comes out, clears up a bit the sky. Then there is afternoon, a lot of variability, a lot of cloud coverage. Then there is the end of the day, you start clearing up, and you have a very clear sky at the end of the day. You can think that this time-lapse movie is just a combination of many, many images. And then you can start doing a clustering where you put in one box all the images where you see 3 peaks. And then you put in another box all the images where you see 2 peaks, at least 2 peaks. And you put in another box, an example, all the images where you see at least 1 peak. And then you put in the last box those images where you don't see any peak, okay? And then you can do some statistics. And the statistics is shown over here. So there are very few times where you don't see any peaks. Of course, the fact that you don't see peaks would never make you believe that all of a sudden the peaks have disappeared, right? You know that there is something else which prevents you from seeing the peaks. And this is pretty much the way you have to think about what we've done with Sagittarius A star. We have lots of images that are all compatible with the data. Some show very pretty rings. Some do not show any ring at all. Some show some kind of ring, but this one, for instance, doesn't show a ring. And then you can do, again, a clustering. You can cluster all of these images according to the properties where the bright spot is. So this is the bottom left, top right, whatever, top left. And again, you can have the statistics. So in our statistics, there are about 2% of the images that do not show any ring. Okay, this is the average of that cluster. But in 98% of the images, you do have a ring. And this is the average of the whole set of images. Now, this means that you shouldn't pay attention so much about the presence of these spots, because these are the average of all of these clusters, okay? One thing you have to pay attention about my analogy is that there is a logical loophole. In the case of the time-lapse movie, the image was in a given precise time window, while the images I was showing you of Sagittarius A star, they are all images over the 8 hours. And they differ just because of the variability in the data, the error bar, if you want, in the data. Okay, so then what is the difference between Sagittarius A star and M87? You can think that, it's like looking at a time-lapse movie, which is either over a day. So, it's a time-lapse which will last just a few minutes in M87. You will have lots of images you can produce out of Sagittarius A. You will have a few images in M87. The images in M87 will be almost similar. The statistic will be, almost uniform. As you can see here, you always tend to see 3 peaks. And this is the same now if you think about the actual images. As I said, all of these images, each of these images is the result of our algorithms in picking up an image or reconstructing an image out of the data. And I think this is really, the most important difference that you have to appreciate between the two. And this final image allows me to go back to a point I made at the beginning. This is the way they look in the sky. They have the right size. They have been scaled so that they have exactly the right size. So Sagittarius A star is slightly larger than M87, but it's amazing that we have been so lucky that they are at roughly the same size. If this guy was a factor 2 smaller in mass, would have been a factor 2 smaller in size, and so we wouldn't have seen anything. We would have seen just a single bright spot. Okay. When you do the comparison, in the case of Sagittarius A star, as I said, you have many more constraints. You have the mass, you have the observation at different frequencies. So this is an example. This is the same simulation at 86 gigahertz or 20, 30 gigs. This is the high frequency, or the 1.3 millimeters. This is telling you about light coming from larger scales. This is the infrared variability. You can see that there is also variability in the infrared, and all of this has to be matched with the observations. And this allows us to kick out a number of models. So just to give you an example on how this works, you take a black hole. This is actually our best bet model. You look at different inclinations. So this is edge on, this is face on almost. Then you have different spins. Okay, you can see that the same object will produce very different images. You can play around with the electrons. This is RI1, RI 160. You can then play with the magnetic field, and you have MAD or SANE simulations. And from all of this, you then have to add 2 angles of rotation, and so on. And out of this, you build essentially 1.6 million images, as compared with the other ones. For M87, it's a factor almost 30. Now, what is interesting is none of our simulation passes the observations. If you put in all of the constraints, none of them passes. The most difficult one is the variability. The timescale for the variability of our simulations is too high. So if you relax the variability, then we can get best bet models. And these are MAD, so strong magnetic fields, prograde, the spin is positive, low inclination, we see it almost phase on, and cool electrons, so R-high 160. That's the best bet model, the model that, apart from variability, matches the observations best.
Sorry, what is the mean value of temperature for the electrons?
So this is, I don't have a number off the top of my head, but this is not real temperature, because these are ultra dilute plasmas. It's a bit like calculating what is the temperature of the corona of the sun. It doesn't correspond to a plasma in thermal equilibrium. I don't know if I satisfied you. Look, unsatisfied. It's not a black body temperature you have to think about. So, but this would be very, very high, of orders of tens of millions of degrees. But this doesn't mean that the temperature of the plasma is tens of millions of degrees. On the other hand, the models which are strongly disfavored, certainly something that doesn't seem to match at all, is small r high, single temperature, prograde, so counter rotating, and seen almost adjoint, I equal 90 degrees. Okay, what about gravity? What can we say about gravity in all of this? Well, you can compare the predictions of Kerr with the measurements coming from Sagittarius A star, which is the red curve, or the M87, which is the green curve. And in the case of M87, we had 2 different values for the masses, and of course, the fact that this one matches the expectation is what allowed us to set a size for M87. If you compare, everything is in reasonable good agreement with Kerr, to 10% roughly. You see that Sagittarius A star has a larger variance, but also has a smaller, this variance, the vertical variance is due to the variability I was mentioning, but as the actual distribution is as a smaller variance, and that's because we know the mass very, very precisely, and this allows us to remove a lot of the uncertainties. And this is another very nice plot, which puts in together gravitational waves and black hole images. This is the fractional deviation delta. So what we do is we say, what is the deviation in the size of the shadow from what we would expect? You can call this delta, and you can say that gravitational wave emission can also be translated into a deviation from the size of a black hole in terms of the ring down frequency that you get. And so now you have a logarithmic plot spanning 8 orders of magnitude. Between these guys and these guys, there are 8 orders of magnitude. These are the prediction of general relativity. And as you can see, everything fits within general relativity, although, of course, there are different distributions. You can see that Sagittarius star has a smaller spread than M87. So everything is consistent. Is this the end of the story? Well, no, really. As I explained, there are degeneracies, and in any theory, which is an observation theory like astrophysics, you have to deal with the general explanation. And the best you can do is you start ruling out those theories that are not compatible with the data. We can't build a black hole in a lab and make sure that it is exactly as the theory predicts. We can only observe it. So you can test theory of gravity, but this is not easy. There are hundreds of different theories, hundreds of different objects you can test. And so you can have either an agnostic approach or agnostic approach. In the first one, I will explain, you don't make any assumption about what theory you're looking at. And in the second one, you say, okay, I want to know exactly whether this object, this black hole with these properties fits the observations or not. Let me briefly tell you about this agnostic approach. It's something that I developed with collaborators. All I need to do this job is a metric, a space-time metric, so a tensor G mu nu in terms of certain coordinates. Then I can do my GRMHD simulation, I can do my radiative transfer, I can calculate geodesics. And so the idea is, instead of having this generic tensor, which is known in general relativity, say Kerr, I produce another metric, which is more generic. And of course, this metric has additional parameters. And if I set these parameters to 0, I end up with GR. There are 2 tricks, mathematical tricks that make this approach particularly powerful. The first one, these are called the RZ and KRZ metrics. The first one is we compactify the radial coordinates. So instead of having the radial coordinates between 2 and infinity, say for spherically symmetric spacetime, it's between 0 and 1. And this allows us to very easily get the asymptotics right and get the location of the horizon very precisely. And because intrinsically, these any representation of this type will have some coordinate singularities, we have a way of approximating our metric functions through an expansion, which is not a Taylor expansion, but is a continuous fraction. And this is a Padé expansion, which converges very rapidly near the pole. The pole is at x equals 0. So if you do this, essentially, then with 2, 3 parameters at most, I reckon reproduce any black hole spacetime that you want. And in this approach, the idea is you make a measurement, you make an observation, you measure what is the values of these AIs. Of course, they're not going to be 0. And then you rule out all of those theories which are not compatible with these coefficients AIs. And as the observation improve, the variability in these parameters will become smaller, and so you get a more and more precise measurement. If you instead want to look at specific objects, what you can do is you can look, for instance, at a Dilaton black hole, you can look at accretion on a boson star, or you can look at, given the size of the shadow, how many black holes of different types are compatible with this size estimate. So let me explain, for instance, a comparison we've done already a few years back between a Dilaton black hole. This is just a possibility. It's a black hole coming from a string-inspired theory, which has an additional field, actually 2 additional fields, the axion and the Dilaton. But we set the axion field to 0. We just look at the Dilaton field. And this is essentially a parameter, an extra parameter that black hole has. And then you can compare, do exactly the same thing I've shown you for Kerr for this black hole, and then compare whether you can tell a Kerr from a Dilaton. And one of the things you have to make sure you're doing is comparing apples with apples. So that means you want to have a Kerr parameter which has a given horizon scale, or with a Dilaton black hole which has exactly the same horizon scale, or has the same photon orbit, or the same ICE-CSIC. Okay, depending on your choice, you will have different dynamics. So you perform these simulations. For instance, you have Kerr black hole on this side, you have a Dilaton black hole. Here, these two are matched at the ICE-CSIC. That's why the horizon size is different. The Dilaton is a smaller horizon, but they have the same ICE-CSIC. And if you look at these simulations, you say, okay, well, they are slightly different, but that's of course not quite the right statement. You know, what you want to compare are images. So you can produce images. We have all the machinery to produce images. And these are the two images that you produce. This is called Kerr, this is with Dilaton. You would say, okay, yeah, I can see there are differences here and there. When you put in the fact that there is variability, these are, you know, the different images that you would get. And you say, yeah, okay, these are also different, but they're also very, very similar. So at the end of the day, you conclude that you can't tell them apart with confidence. So right now, this is a true statement. We cannot tell apart a Kerr black hole from a black hole of another theory, at least, you know, not with great precision. What about other objects that behave?
We have like a couple of minutes.
Yeah, okay. What about other objects like a boson star? I will just go quickly through this. In the case of a boson star, you can't really tell the difference because you can see that the shadow is considerably smaller in the case of boson star. I can explain why that is so, but let's say the bottom line is that it is possible to distinguish boson stars from black holes, and in fact, our observations have ruled out certain classes of boson stars. This is the other example I was mentioning. You can have, you know, a Reisner-Nordstrom black hole. You can have a Badin black hole, a Frolov black hole, Award black hole. These are all black holes which have additional properties, additional parameters. And according to these parameters, you will have different shadow sizes. We have measured a given shadow size, which is given, you know, essentially by this white region over here. And then you can, anything which is outside of this white region is incompatible with the observation. So you can see that most black holes stay still in the white region, but there are some black holes like this EMD1, which for some certain properties of their charges are incompatible with the observations. And here you can see how these changes with spin. Okay, conclusions. I try to explain that imaging supermassive black hole is a rather complex endeavor. You need to have a lot of expertise from VLBI, taking the data, producing the images, and then interpreting the images. We have studied accretion over the last few years more than we studied, and we learned about accretion more than we've done over the last 30 years, I would say. We are exploring alternatives to Kerr black holes and boson stars. So yeah, boson stars can be distinguished, other black holes cannot. I think, you know, one of the important things that EST has done is provide evidence that there are supermassive black holes at the center of the galaxies. Well, at least two galaxies have two supermassive black holes. By inference, you can extrapolate. But according to me, the most important contribution is that EST has made the event horizon, which is a concept, a mathematical definition, something you can test. And so all of a sudden, we have a tool to start ruling out theories which otherwise would not be ruled out just because they are mathematically plausible and correct. Thank you.
Thank you very much.